Welcome to EDU World Space.
So in this question, we're asked to calculate how much work is required to launch a spacecraft of mass m from the surface of the Earth and place it in a low Earth orbit. And basically the meaning of the low Earth orbit is just that the altitude is very low in comparison to the radius of the Earth. So essentially in terms of energy, we're going to end up ignoring that small change in radius due to the altitude. So let's start off with tackling this part A, and then we can get to the rest of the parts. So work done is basically going to be equal to the change in the kinetic energy plus the change in potential energy. And in this case, we start off with no kinetic energy, and we're going to end up with some kinetic energy due to the orbit. So I'm going to label that 1/2 mv squared. And then we are going to have a change in kinetic energy due to the fact that we are going from the Earth's surface to this slightly higher altitude. So the final potential energy is going to be negative GMM over RE plus R. And here I'm taking R to be just that small amount of extra altitude. And the initial potential energy is going to be GMM over RE. Here I've put a plus sign because we've got two negatives there. We've got the minus UI, or the minus initial gravitational potential. That combines with the negative that's already there and creates a plus. Now, something else that we can substitute here is an expression for VF, because we know that the object is going to be orbiting. And so we know that we have an expression for orbital speed based on some of these other variables that we're already using. It's GM over RE. Or in this case, since we're orbiting at that radius that includes the extra altitude, it would be RE plus R. And then that gets squared once we plug it into for VF squared. So we end up with an expression that looks like this. GMM over RE plus R. Look familiar? So we can definitely do some combining here, right? So we've got minus GMM RE plus R plus GMM over RE. Now, the point of them making a big deal about the low Earth orbit and how it is very small in comparison to the actual radius of the Earth is because we're going to make an approximation here. So we're basically going to say, okay, RE plus R, since R is small, the altitude is small, we're just going to say RE plus R is approximately RE. And so once we do that, we basically get a bunch of the same terms. So we're just replacing RE plus R with just RE. Okay, so over here we get a cancellation. And again, this is an approximation, so it's not exactly correct, but this is what we end up with. So we have GMM over 2RE. And that is approximately the work that needs to be done in order to place an object in a low Earth orbit. So this is the final answer for part A. In part B, we're asked to calculate the minimum amount of additional work required to move the spacecraft from the low Earth orbit to a very great distance from the Earth. And we can ignore, a whole bunch of things, gravitational effects from other bodies. So let's go ahead and do that. Now we're going to do the same thing here in terms of work done. I'm going to do the change in kinetic energy plus the change in potential energy. And I'm going to use the expression here, 1/2 GMM over RE plus R, for the initial kinetic energy now, because that's the energy that's associated to the object in the circular orbit, at least in terms of kinetic energy. The final kinetic energy I'm going to put as 0, and I'll explain why that is in a second. So the reason we're putting the final kinetic energy as 0 is because if the object or the spacecraft is going a very great distance from Earth, it's going to end up using all its kinetic energy to get further and further away, and so it ends up with 0 kinetic energy. So this is the change in kinetic energy, and then the change in potential energy is going to be similar. So the final potential energy is going to be 0, because if you think of GMM over R, if R is really, really big, then that's 0. Okay, and then the initial kinetic energy, the initial potential energy is going to be GMM RE plus R, and there is a minus minus here, so I'm going to put a plus. Okay, if you don't understand that, that's just because it's UF minus UI, and this term already has a negative, so there's 2 negatives there. And yeah, we're basically home free now. We can add together the negative 1/2 with the positive 1, and we get 1/2 GMM RE plus R. Or if we're thinking of, R being really small, we can just replace RE plus R with RE again. And we basically get the same expression, GMM over 2RE. And so the fact that we get the same thing for A and B is what kind of justifies Part C. So in Part C, it asks us to justify the statement, in terms of energy, low Earth orbit is halfway to the edge of the universe. So basically, we need a certain amount of work to get into a low Earth orbit, that's GMM over 2RE. And then to get from that low Earth orbit to the edge of the universe, we need, again, another packet of GMM over 2RE. So each of those stages uses the same amount of energy. So in terms of the total energy to get to the edge of the universe, the low Earth orbit is halfway there. I don't think I really need to write anything for that. So that will be the conclusion of this video.